Now the next module is regarding the determinants, and this is the concept which is much familiar to you. So the determinants are, regarding this determinants, we need to study some basic things. So determinants are already learned, so I don't think much of the work is required here, so we can go a bit fast. So the page number 225 onwards it stands. So please have a glance on this. The basic properties of determinants we need to see. Determinants are of square order, whereas the matrix will be of any order m into n. So regarding the determinants, we'll see some of the uses and their properties. The first one is the test for invertibility. If the determinant of A is 0, then A is singular. If it is not equal to 0, then it is invertible. So we know how it is done, and even the solving of A minus lambda I for eigenvalues. The next one is regarding the determinant of A equals the volume of the box in n-dimensional space. The edges of the box come from the row of A. The columns of A would give an entirely different box with the same value. So the determinant of A equals, of course, a volume of n-dimensional of what order it is, and these edges of the box come from the rows of the A. So just we can see, if the determinant is having its A11, A12 and A13, then this edge would be represented by A11, A12 and A13, and the other edge is represented by A21, the second row, and this is by third row. The simplest box can be the cube with all its three dimensions like dx, dy and dz. So its volume would be dx, dy, dz, and if we go for finding its total amount of area within it, it is x, y, z, or it would be dx, dy, dz in terms of differential components. And in cylindrical coordinate system, if x is r cos theta, y is r sin theta, and z is z, when we see the three-dimensional things, we'll get to know how these arise. But when we go for their equations, so we can write it in this form. So cos theta, sin theta, 0. If x, y and z are so, then we go for writing the Jacobian determinant. The Jacobian determinant in three-dimensional system is given in this fashion. So Jacobian J is dx by dr. In the first column, differentiation happens with r, differentiation by theta in the second, and differentiation with z happens in the third column. So when we differentiate these values, let's think that x is equal to r cos theta, r sin theta and z. So in all these columns, these would be x, y, z, x, y, z, x, y, z. So r cos theta's differentiation with respect to r would be like r, differentiation of r is 1, cos theta remains, and differentiation dy by dr. So r goes, actually it is r sin theta, it becomes just sin theta, and differentiation, there is no term z, there is no z in this, there is no r in this z term, so differentiation of this dz by dr is going to give 0. So in this way, these all components are differentiated and we get this matrix. Then the next point is regarding the determinant gives the formula for each pivot. Theoretically, we could predict when a pivot entry will be 0, requiring row exchange from the formula determinant is equal to product of pivots. So which indicates that when we exchange any row of the determinant, when the row position is, when we are having no pivot element in that one, if that place is 0, we can go for row exchange. Even though we do some row exchanges, then also the product of the pivots is going to remain same, and determinant is equal to product of the pivots. The meaning is when we exchange the rows of the determinant, when we exchange the rows of the determinant, for example, it is a determinant if there is no pivot element here. Actually, this has to be a non-zero element. If it works out to be 0, then if there is, it has to be a non-zero. If there is 0 here and if there is a non-zero element here, we can exchange the third row and second row. Even after doing, there is no change in the product of the determinant, is the statement of that property. Then the next one is the determinant measures the dependence of A inverse B on each element of B. If one parameter is changed in an experiment, then, or any observation is corrected, influence coefficient in A inverse is the ratio of determinants. So this happens if any of the value is changed. So it would be the influence coefficient is, so when we are doing the experiment, this kind of property would be, this kind of use, these are the properties and also these are the uses. The main properties we'll see, and the syllabus begins from the properties of determinants. So as these are pretty easy, we can go for them just from the book itself. So let's consider a determinant. Then the determinant value is given by, it is the opposite elements A into D minus C into D. So a determinant of a matrix we can write, determinant of A we can write, or we can represent in this fashion. Its value would be AD minus BC, and let's see some of the determinants identity matrix. So determinant of A we can write, or determinant of A in this fashion. So determinant of I is 1. So determinant of I means it represents the value of that matrix. So when we represent this determinant of 2 into 2 matrix, so which looks in this fashion, its value is 1. Similarly, of 3 into 3 order, its value is 1. The determinant changes the second property. The first property is the value. Determinant represents a value, and it can be referred as determinant of so and so letter. And the second one is the determinant changes sign when two rows are exchanged. Means, let's say our determinant is given by A, B, C, D. If we exchange these two rows, if the second one becomes first and first one is second, so it's the product value will become CB minus AD. So to give the same value of the determinant, its sign will be changed. So this is the most important property of determinants. Now the next property is regarding, let's consider a matrix which is A plus A with A dash, B plus B dash, and C D. Now whenever such cases are there, then we can write this matrix as the sum of A, B, C, D plus A dash, B dash, C, D. So that has been indicated in the third property. That is, suppose A, B, C are the same from the second row down, and if the things C and D are same, A, B, C, D are same, and row 1 of A is linear combination of A, it's a linear combination of first rows of B and C. Now we have A, B and C. Then rule says determinant of A is same combination of determinant B and determinant C. Means if A, B and C are the three different determinants, then in these cases A plus A dash is there, which is a linear combination of A and A dash, B and B dash, and these two, the lower row remains the same. So in these cases we can write this A is equal to B plus C, and if there is a multiplication by some value with any of the row, then we can take that element outside. And even determinant of BC is equal to determinant of B plus determinant of C, we can write. The next property is regarding if both the rows are equal, means if the values are same in both the rows, then the value of that determinant is equal to 0. For example, if AB, AB are the rows, then AB minus AB, which will be 0. The next property is regarding the subtracting multiple of one row from the other, as we are already familiar in the last chapter. Suppose ABCD is our matrix. Suppose ABCD is our determinant. Then if we want to operate, let's say ABCD is our determinant, and if we want to operate, then we can change the first row as well as we can operate the second row also. So if we want to work on it, then we can write it as the first row is, so as we are familiar with those operations, even though we do the operation, so let's say A is being written as, so the first row is changed as first row minus L times the second row. So when we do this, then also the value of this determinant will not change, because this term into D, wherein this term is extra, and even minus of this C into the same extra term, that is C into B minus LD, which will make this determinant value as same. If a determinant is having, the next property is if a determinant A has a row of zeros, if there is a row of zeros, then the value of the determinant is 0. The next property is if A is a triangular, if A is triangular, then determinant is the product of A11, A22 and so on of the diagonal entries. If the triangular A has ones along the diagonal, then determinant A is equal to 1. So such kind of a matrix, such kind of a determinant is referred as a triangular matrix. So it makes a triangle. Similarly, the upper triangular matrix, this one is, and this one is the lower triangular matrix, and the product of this one is A into D. Even this product is, this value of the determinant is A into D, and if it has 1 along the diagonal elements, certainly its value would be determinant of 1, and the same is been proved, because A11, A22, A33 and all, and if the diagonal elements, they all are equal to 1, the value has to be 1. Then the next property is if A is singular, then determinant of A is a 0. If A is invertible, then determinant of A is not equal to 0. So for that, let's consider singular matrix ABCD is not invertible if and only if AD minus BC is equal to 0. The proof of that one is bit easier. If A is singular, then the singular matrices or the singular determinant, they go 0 because the rows will be linear combinations of the other. And if it is so, then the value of the determinant U, even after reducing the determinant A, will make it as 0. The determinant A or determinant U, the reduced form, will go 0. And if it is 0, then it is not at all invertible. If A is non-singular, then elimination puts pivots. Pivots will be there because the rows are not linear combinations of the other rows. and as they are not linear combinations, there exist pivots, and let the pivots be d1, d2, etc. How many number of rows and columns are there? If it is a n into n matrix, then d1, d2 up till dn exist, and in those cases the determinant A or the determinant U is equal to d1 into d2 into so on up till dn. Depending upon the number of operations, row or column, the plus or minus sign will be there. So depending upon the number and what will be the value of the matrices and determinants, the values plus or minus may be there, but determinant will be non-zero, and when it is non-zero, then its inverse exists. The next property is regarding determinant of AB is the product of determinant A times determinant B. It says that determinant AB is always equal to determinant A times the determinant B, which is true. So for example, AB and CD is A and EF and GH is B. Then AB is A into E plus B into G. As we know the multiplication, it is AE BG, then it would be AF BH in that way. So when we go for this, it would be that times. After solving this determinant A and determinant B, and when we solve this AB, then we can verify that whatever is the multiplication of this one, so we get some value out of this matrix, even out of this matrix, and whatever we get the solution out of this, it will be A times the multiple determinant A times the determinant B value. Then the next one is regarding determinant of A inverse. Determinant of A inverse is equal to 1 by determinant of A, because we know the determinant of A and determinant of A inverse, the product of this is equal to determinant of A into A inverse, which is equal to determinant of I. A into A inverse is I, and is equal to 1. So if determinant of A inverse has to be 1 by determinant of A. How does the product determinant A, determinant B, the product of determinant A and B is equal to determinant of AB, how it can be derived or how it can be done in different ways is being explained over. So the next one is the transpose of A has the same determinant as A itself. So if we have a determinant A and if we find its value, its determinant, then if we take up the transpose of the determinant, wherein rows will be converted into columns and vice versa, now A, B and C, D, it is A transpose. The determinant value of this A as well as A transpose would be same. By using the above said properties, if determinant A is equal to half, then what is determinant of 2A, which will be, by using A into B property, we can write, so which will be 1 by 2 into 2, and if it is determinant of minus A, then it would be minus of that. If it is A square, then it would be the product of those, and if it is A inverse, it is then 1 by 1 by 2. So in that way we can go for solving. Even by referring the solutions also we can cross check the problems, these exercise problems of 4.2. The next point is regarding the cofactors. So we all know how to find the cofactor in the previous classes. So the cofactors of each of the element can be found. For example, the cofactor of this A11 would be this A22, A23, A32 and A33. So this determinant of A12, it would be these two elements and these. So we need to leave the row in which R element is there, even the column in which R element is there, except that when the other elements are considered for finding its cofactors. So as cofactors are known, let's go with the problems of those. A 4 by 4 second difference matrix A4 has only two non-zeros in row 1. Use cofactors. The cofactors are found determinant A by cofactors. So it is, suppose AI1, then CI1 it is, like AI2, CI2. So I and J, so for they can be any values. So delete row I from column J. So the process is already known. Already it's known. Cij is equal to, the formula for cofactors is minus 1 raised to I plus j, determinant m I j. So how to find for that? Minus 1 raised to, suppose if we are finding it for the first one, then this first element, it would be C11. So for this, minus 1 raised to 1 plus 1, it is minus 1 raised to 2, which will be 1. And determinant of Mij is nothing but, except this column and this row, the rest of the elements are considered, as we can write here. C11 is determinant A3. So it is of order 3 this way. So all this minus 1, 2, minus 1, 0, minus 1, 2, minus 1, and this way the cofactors are found. So depending upon the element, they can be like minus 1 raised to, depending upon that sum, it can be plus or minus, and the cofactors have to be found for all the elements of the matrix or determinant. And on these the problems will be asked. And C12 is minus 1 raised to 1 plus 2. So minus 1 raised to 3, which will make it as positive. Then we can write the cofactors of this. The cofactors of this are given. So C1, 2 it is. So in the first row, the second element for this would be this column and these all. Minus 1, 2, minus 1, 0, minus 1, 2. So the cofactors have to be written for the individual elements. Then on this, the exercise problems would be like, for these matrices, find only non-zero term in the big formula A and B. There is only one way of choosing 4 non-zero entries from different rows and different columns. By deciding even or odd, compute determinant A and determinant B. The determinant of A and B is to be found, and some true and false. So you'll get the solution. So please refer the solution link. So when usually the first problems are like not being locked. So these are the basic things. Let's go through this.